Okay, so now we're going to talk about shapes and connectivity of molecules. And we're going to introduce something called Lewis structures for molecules. And we're going to derive really a lot of value from Lewis structures because they're going to give us lots of information with just a few pencil strokes. And we're totally ready for this. So let's go here, grab a marker, and say our learning goal for this section is to draw the Lewis structures for molecular compounds or polyatomic ions, right? So a Lewis structure is, here's a picture of a Lewis structure here, another picture of a Lewis structure here, right? And it gives us how atoms are bonded to each other, tells us a lot about it. So the simplest molecule, we'll start with this one, is H2. Now hydrogen, you may remember, has got an electronic configuration of 1s1, right? That's the electronic configuration of that. Now we're going to draw the Lewis structure of the hydrogen atom as hydrogen, the symbol, with the dot because it has one electron in its outer shell. Now it only has one shell, but its one shell is the outer shell. And so we'll see later that atoms that have multiple shells have an outer shell, right? And it's the outer shell that interacts with the other atoms. So we're going to put the outer shell electrons outside the symbol here, like I did. And that is what a hydrogen atom looks like. Now, what happens is a hydrogen atom might look like that, and another hydrogen atom might look like this. And this hydrogen atom says to this one over here, hey, I've got a capacity for 2 electrons in my outer shell. If I can borrow your electron, then I can, and I mean share it. I'm just going to share it. I'm not going to take it, right? And if I can share it, then I'll have 2 electrons in my outer shell. So what happens is they get closer to each other, right? And in time, they get close enough that, right, that the 2 electrons feel to this hydrogen atom like they're in his shell. And these 2 electrons feel to this hydrogen like they're in his shell. It turns out they're in both their shells. They are shared, okay? And since they're shared, and we draw that, by the way, we draw that as a bond. And since they're shared, then both of these hydrogens have their valence shell filled. And so we would say these electrons are covalent, right? They're in the valence shell of this hydrogen, and they're in the valence shell of this hydrogen. So they're covalent, right? And so covalent or shared electrons we call bonds, right? And that is a bond between, that's how we would draw the Lewis structure of a hydrogen molecule, like this or like this. Those are both legitimate Lewis structures. I sort of just went through this slide right here, a nice figure in your book, talking about how this happens. I just went over that in a previous slide, so I'm going to skip it. Let's move on and say a molecule is represented by a Lewis structure in which the valence electrons of all the atoms are arranged to give octets. Everybody wants their outer shell filled, right? Which is perfect. So the shared electrons, or bonding pairs, I just sort of went over that in a previous slide, are shown as 2 dots or a single line between atoms. The non-dot bonding pairs, or lone pairs, are placed on the outside of the atom. So there's like a non-bonding pair for nitrogen, and here is ammonia. This is the Lewis structure for ammonia, okay? So a molecule is represented by Lewis structure in which the valence electrons are arranged to give octets, which we've already said now a couple times. To draw the electron dot formula for a fluorine molecule, right, we're going to do something very similar. We're going to draw a fluorine atom and another fluorine atom, right? And they're both going to say, hey, I need 8 in my outer shell, but I only have 7. If I can borrow one from you, that'd be awesome. So this fluorine says, hey, look at that. Let's come with a different color. I like your electron. If I can borrow it, and there's that same electron right there, right? If I can borrow that electron, then I can have 8 in my outer shell. And he does, right? So they get close enough where both of these fluorine atoms can feel those 2 shared electrons. And those shared electrons are here. They make a bond. It's the same. We sometimes draw it as a stick. We sometimes draw it as dots. Okay? So this is a covalent bond that is formed when 2 fluorine atoms get close enough to share their electrons to fill their outer shell to make an octet. Okay? So we draw it like we draw the symbol like this. If we were to draw a picture of it, it might look like that, right? We've got two spheres that are sort of pushed into each other, okay? And that is a diatomic molecule that is fluorine. Now, it turns out there are 7 elements. I almost said 8. There are 7 elements that make diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Can you see the sort of backwards? No, this is actually like a 7, right? Can you see that 7 or a backwards gamma? See that? In hydrogen. That can help you memorize which ones they are. If you can see a backwards 7 here, I'm sorry, not a backwards 7, a backwards gamma or a 7, and the hydrogen up in the corner, then that may be a good way to memorize which atoms make diatomic molecules. Okay, now this is kind of a neat to appreciate that the number of electrons of non-metal atoms, the number of electrons a non-metal atom shares, and the number of covalent bonds is usually the same. Okay, and it's always done to achieve a stable electron configuration. Right. So, for example, hydrogen makes 1 bond because it has 1 extra electron to share. Now, by the way, hydrogen and boron do not form octets, so watch out for that. Okay. We've already talked about boron, hydrogen extensively. I haven't said anything about boron at all, but it does not typically form an octet. Boron has 3 electrons in its outer shell. It can make 3 bonds. Carbon has 4, or really wants to borrow 4 to make 8, right, in silicon, and it makes 4 bonds. Nitrogen has 5, and so it wants 3. It wants to borrow 3, and it makes 3 bonds. Oxygen has 6 in its outer shell because it's group 6, right? So oxygen wants to borrow 2 electrons, and therefore it makes 2 bonds. Fluorine, chlorine, bromine, and iodine are in group 7, right? And so they only need 1 electron to make an octet, and sure enough, they make 1 bond. All right, that's not a coincidence. So let's talk about now drawing Lewis structures. To draw the electron dot formula for methane, you'll be given a question, okay? And the question goes like this. Draw the electron dot formula or the Lewis dot structure for methane, right? And they'll give you the formula, CH4. So you say to yourself, all right, well, first of all, let's draw the Lewis symbols for the atoms. There's carbon, here's hydrogen, right? And so I'm going to say, well, these guys are going to share and make a bond. But wait, I have 4 hydrogens, right? So, aha. And there's another bond right there. Another one over here. You get what's going on, and you end up with a structure that looks like this or like this. Okay? The carbon needs 4 hydrogen atoms, really needs 4 electrons to form an octet, but that'll work nicely if you give it 4 hydrogen atoms, each of which can lend an electron, right? Carbon needs 4 hydrogen atoms. 2 bonding electrons between carbon and hydrogen can be drawn as a line, which I've said before. And the central atom is the atom in the formula with the least number. Let's see, the central atom is the atom in the formula with the least number of atoms, okay? In other words, CH4, right? CH4 only has, carbon only has 1 atom, and so it's going to be the central atom. Okay, electron dot formulas for common molecules such as methane, ammonia, and water are shown for you in your textbook, table 6.14. There's methane we just saw. We saw ammonia in a previous slide, and water. You may have seen that sometime before in your life, maybe a high school chemistry course. That's the electron dot structure or the Lewis dot structure for water. Okay, let's wrap this up now with a learning check and then one final comment after the learning check. So here's the learning check. Pause the video and draw the Lewis structure for PCl3, phosphorus trichloride, and then compare your answer to mine. Okay, so I'm going to suppose that you pause the video, and I'm going to find phosphorus. Phosphorus is in group 5. Phosphorus is right here in group 5, right? See it? So it's got 5 electrons in its outer shell. 1, 2, 3, 4, 5. Okay? And chlorine is in group 7, and so it's got 7 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right, you see what I'm doing with this? I'm saying, all right, there's going to be a bond here, and a bond here, and a bond here. And there it is. That is the Lewis dot structure for phosphorus trichloride. You might have drawn one like this. Phosphorus, getting sick of making big dots. So I'm going to make some small ones here. Hopefully you can see them okay. Oops, I didn't see that one. Okay. So these are both legitimate Lewis dot structures. Well, they're really kind of the same thing, aren't they? Legitimate Lewis dot structures for phosphorus trichloride. Now, finally, let's round this conversation out by talking about double and triple bonds. So double bonds occur when atoms share two pairs of electrons, okay, and they form when there's not enough electrons to complete octets, right? So carbon, for example, and oxygen, carbon dioxide, doesn't have enough electrons for everybody to have an octet. So what happens is they say, let's just share two, right? And then carbon's got its 8 electrons in its outer shell. Oxygen's got its 8 electrons in its outer shell, right? And there's the other oxygen with its 8 electrons, right? So that works nicely. Same thing happens here. You might get a triple bond, right? There's a triple bond. And so nitrogen's got 8 electrons in its outer shell. Carbon's got 8 electrons in its outer shell. All right. So we'll wrap this conversation with a couple exceptions to the octet rule. First of all, boron, which I told you before, boron does not make. Where's boron here? Doesn't say it, does it? Doesn't say it, but boron does not ever get 8. It has only 6 in its outer shell because it's so small. So it's just a weird exception. If I were you, I would just memorize it. Extremely exceptional, right? We're used to things having 8, right? Except hydrogen, and we've seen hydrogen so much that it doesn't bother us. Maybe hydrogen only has 2 in its outer shell. Boron has 6. Its outer shell is not filled. But nonmetals such as phosphorus, sulfur, chlorine, and bromine, and iodine can form compounds with 10 or 12 valence electrons because they have a bigger outer shell. Their outer shell is 3 or 4 or 5. And since their outer shell is 3 or 4 or 5, they have a capacity for more, right? So we will see some, with these atoms, we'll see some that have 10 or 12. All right? The sulfur atom, for example, it typically has an octet, but in SF6, it has 12, okay? And that's, again, because its outer shell is 3, it has a capacity for some extra electrons. All right, I don't think that's all we're going to say about that.